Okay, welcome everybody. It's a real pleasure to welcome you again here at the Mathematics Education Seminar. And well, our speaker of today does not need any introduction because he is, I think, either your collaborator or a colleague. It's Michiel Doorman. He is going to talk about inquiry and is going to provoke discussion and deep thoughts about it. So the floor is yours.
Yeah, I hope to do that. Well, thank you for being here. And so the title is Why Promoting Inquiry Mathematics Teaching Did Not Work. And Frans already asked me, so why did you put promoting there and not just why inquiry-based mathematics teaching did not work? And maybe that, that might also be topic of discussion. So in general, I'm quite skeptical about it, although I'm also trying to support it. And so it might be a nice discussion in the end, so and I think we will have time for discussion. The content of the talk, well, first I will elaborate a bit on IBL in mathematics, because it originates mainly from science education. How to, to learn to do inquiry is in science education, I think, more obvious and more explicit part of the curriculum than in mathematics. And it's only recently, the last few decades, that it also became part of discussion for mathematics education. Then quite some time I will use for talking about two projects I was involved with one on a professional development course for inclusive science and mathematics education. That was the MASDIV project, almost finished, not final yet. And the other one, together with Rogier, is the Meria project, and that was focusing only on mathematics and designing inquiry-based mathematics lessons and also implementing them. And then that project was inspired by realistic mathematics education and the theory of didactic situations. So we'll also pay some attention on the latter starting point of that project, because I hope you are all familiar with realistic mathematics education or the ideas behind it. Then the third part of the talk will be a kind of reflection on what we learned from these projects, but also there I try to involve other studies and kind of mirror or compare our findings with what these studies say about inquiry-based learning and the implementation and the challenges. And in the end, well, I hope we will have time for the discussion on the title of the talk. Okay, first, well, I said ABL in mathematics is not really obvious, so I have a little practical for all of you. That is inquiry-based, I would say, in a way. It's about defining, and my question to you is get pen and paper, or when you don't have pen and paper at hand, try to do it by heart. So write down the definition of a polygon individually, and then take a minute. A polygon, I hope you all know what a polygon is, and write down a definition of how you would define a polygon. But okay, I think now is a good moment to exchange your definitions, so go to a neighbor. Okay, I noticed that already a few of you weren't sure about what a polygon exactly is, and some of you already learned now something about what is a polygon. So I'd like to write down at least one definition. So what definition did you come up with, Arthur and Annemiek?
Decided because there are things that are unfinished, so to speak.
Okay, an attempt?
Well, a closed, flat, geometrical figure. At least 3 straight.
Yeah.
Straight. Yeah. Okay.
We're not quite happy, but it was in the direction.
One other definition. Who has really a different one? You?
I have to translate it. A two-dimensional area captured by straight.
Two-dimensional area
Captured on sloping. Enclosed.
enclosed.
By straight segments and any the segment between any two points belongs to the area. But we didn't quite agree about the last sentence.
It belongs to the area, or well, okay. Okay, so then the final part of this activity is now I'm going to show you a few figures and just check whether these figures meet your definition or not, and to what extent it needs to be improved. Well, and of course here are, we can do this again individually and discuss it, and the purpose of the task that we really learn to watch at different kinds of polygons, try to sort them, which belong to what we call a polygon, which don't belong, and then try to find a definition and see of what kind of parts you need for this definition. And why this activity is kind of inquiry-based activity, it's that also in mathematics it's important to learn defining and to involve students in this defining, because that's something we we hardly do within mathematics, I think, in this kind of activities. So what really is a polygon? How could you define it? What kind of concepts do you need for defining it? And are we all sure about these concepts? Are we sure about what a segment means? What a geometrical figure is? Yeah, a flat geometrical figure. That sounds rather general. And so when you do this kind of activity, you immediately notice that there are all kinds of implicit elements in what we do with mathematics, which we don't make explicit, and I think that's part of, teaching it in a way that we know what kind of procedures students need to learn and what kind of calculations are necessary, and teaching is often focused on these procedures and calculations and not so much about the real concepts that are behind it. So one other example of, what also I think is part of inquiry mathematics is that you look at statements. It's a rather old example, and that you think of these statements whether they are never true, sometimes true, or always true. And we are in the end of the afternoon, so we could have a look at one of them. For instance, this one, which I like, and it's always nice. A pentagon has fewer right angles than a rectangle. So is that never true, sometimes true, or always true? So could you think about that for a few seconds? At least I see one or two drawing, because that's what you need to do. You need to start drawing. And this is also something that we also notice when we work with teachers, that when you are in inquiry, often you are in a situation where you're not sure yet about the answer, and teachers are very hesitant in making their thinking explicit when they are not sure about the answer. And so they are aware of the fact that you can be afraid of making mistakes. And this is a kind of culture we also need to be aware of, that this culture is there. We always expect our students to make their thinking explicit, but it's not so easy. And it's something you need to learn, that when you are not sure. Okay, so who has an idea of an answer?
Depends on your definition of pentagon.
Okay, so why?
If you would consider,
You can come draw.
So for example, do we consider this pentagon. No, because of this. Sorry, I was drawing in my mind and I made a mistake. Because this is clearly a pentagon with 6. So I don't think we will.
These are 5 corners.
Yeah, it's 5 corners.
Oh, you're right. Yeah.
Yeah, it depends.
Section we ignore.
Yeah.
Okay, but then we don't call this a right angle. So then we still have fewer ones. Okay. Then I changed my mind and I think it's always the case.
It's always the case. Probably it's always the case. You also agree? What kind of argument would you give for it? Why are you convinced?
I tried to construct a pentagon with 4 right angles, and I didn't make it.
Okay, well, of course, it's dependent of your definition of pentagon. Yeah, Rogier?
I think, well, I think that you were almost there, right? Because as long as you make angles of 90 degrees, you stay, you go either north or south, or west or east. And then it seems like if you're going to not do that at one point and go into one of the directions that's not that, then at least at 2 points you're going to end up not going north, east, south or west. The starting and the ending point of that.
Yeah. Okay, so it's a nice kind of reasoning from the construction, how you construct it.
Yeah.
What you can also do is have a look at, well, there is a formula for adding up the angles. You know that when you add up the angles in a pentagon, you always get a number, and when you start reasoning from there, you can also see that it's impossible to have at least 4 right angles, because then you don't have any degrees left for the 5th angle. Okay. Well, the idea of this activity was to let students become aware of the importance of the difference between examples and counterexamples. That as soon as you have one counterexample, you are certain that something is not true, and examples are not enough to be sure that something is always true. And so this idea is also part of inquiry, I think, in mathematics, and a very valuable activity that we hardly do in practice. I think also this kind of become aware of the value of examples in trying to support or attack a theory about something. Okay, a final example that I already used quite some time that also shows a kind of difference with regular textbook tasks. So this is a textbook task about a situation and a medicine that you can take a daily dose, and then part of it leaves the body daily, and then the question is what will happen during several weeks when you take the medicine, how much of it stays in your blood. And when you see such a kind of context being used in the textbook, then what often happens is that you have the first question that asks, so how much of the drug is in the blood in the patient after 1 day, so that you do one calculation. Then there is a kind of table that you know the calculation procedure, so you can do it for more days. And then often there is a kind of formula given, show that you can use this formula. And in the end, the final question is what is the maximum amount of the drug that can be reached? And actually, this is the initial question. Because this is the question that belongs to the story, but for the students, and that's the strategy they often learn from dealing with the textbooks. They don't look immediately at this question. They even don't read the first part. They just start with the first question, how much of the drug, and then going to see whether they have the information here, because the information must be here to solve this first question. It's the easy question. And then start from there. And so almost don't think about the problem as a real problem. Don't think of the strategy of solving this real problem, because the textbook is doing the thinking, and they just follow stepwise the activities and have confidence in the textbook that when they follow these steps, they always end up with the final question and are able to have all information there to answer the final question. So another way of doing it is by just providing the initial situation and then just ask the students to investigate what happens. And Of course, you can provide them with all other questions, like what happens when you skip one day, you forget one day to take the medicine? Is it then allowed the next day to take a double dose? Is that a good choice, or can that be dangerous? And things like that are, well, you could discuss in advance with your students what's going on there and then let them work on it. And this task is already quite old, and actually this was first what we designed in the end of the 90s for the study house, where problem-based practical assignments were needed for education, and later on we made this as an example to contrast it with what traditionally happens, and this really worked quite well. I don't know, did you ever use it, or?
Still, I have.
Still, still, yeah.
You assume that you take it at one moment, the daily dose.
Well, yeah, then this formula doesn't fit, you mean? Yeah, so in this version, you can have really a lot of different kinds of answers. That's also what we did see. We have seen students taking it, defining it for 500 milligrams, 3 times 500 milligrams, and then ending up with a formula that gives a completely different, what do they do? The new equals, so they ended up with this formula, and then you get, when you calculate that, you get a real other maximum level, because and that doesn't really fit with the information. But we saw also students doing this, but not with the formula like I do it now, but just by calculation and then extending the calculation, and some of them come with a formula, but not all come with a formula. But what they discover is that they come with different levels. And then you have a really nice starting point to talk about, well, what did you do differently? And how do you come with different levels? And so that's, and then it's interesting to see how you can derive from, when you can describe your calculation procedure with one of the formulas, you can also calculate what kind of limit level you will end up with, and that's a nice next step for of this problem. Yeah. Okay, so just a few examples to show that doing inquiry in mathematics education can be valuable and really add something to, well, what traditional educational practices, I think, show. So the idea behind this is that inquiry-based learning is kind of inspired by the inquiry cycle, so that you involve students in one or more phases of inquiry. That can be learning to question a situation, learning to formulate hypotheses, learning to explain, to set up a systematic way of finding answers, and to share conclusions with others, and to be able to pose new questions when you've solved something. And in general, goals are often mentioned: raising interest, create ownership, just let students, because they become involved, they are owner of the problem, a kind of deeper learning, and also developing inquiry skills. They learn to do inquiry. But you need, well, good teaching materials, something else than the traditional textbooks. You need a kind of other classroom culture and many other things. And these are also topics that will return later on also during this presentation. A rather nice definition, I think, was by Michiel formulated. Inquiry-based instruction is an intentional student-centered pedagogy that challenges the learner to explore concepts, ideas, and or phenomena before formal explanations are provided. So let them involve in doing inquiry before you give the formal rules and procedures. And then in mathematics, you could say this definition is trying to, well, let students act as a scientist, learning about science, but also learning by modeling. And this inquiry cycle, I think in mathematics we are more familiar with the modeling cycle that has some similarities but also some differences. And here's one picture of the modeling cycle by Werner Bloom, and there are also others, that you have a kind of problem in reality and you need to try to make a model of it, mathematize it into a mathematical model, do your calculations and try to interpret it in terms of the original situation and come up with a new question or new ideas. And there are similarities, I think, in general with the inquiry cycle. So learning by modeling has many connections, I think, to learning by inquiry, although there are some different emphasis. We can return to that in the discussion if you like. Good. In one of the projects, we try to define IBL and say, well, it's difficult to define it in one sentence. And this was in the Primas project. And there was also a European project, and we said there are many dimensions when you want to define IBL related to the kind of activities by the students. That was the former definition also of Michiel, of the way students are confronted with inquiry before the formal definitions. But it also has to do with what you value as outcome, that it's not only conceptual procedural knowledge, but it's also curiosity, it's understanding the nature of science and the nature of mathematics. It's also about preparing for lifelong learning, because you learn to learn. That you should also value as outcome, and when you don't value those outcomes, then it might already be questionable whether you would like to implement IBL or implement it in an intended way. Teacher guidance.
This is the concepts. I mean,
sorry?
you would also
Yeah.
reach some goals. So where are these?
Yeah.
I mean, this is more the.
Yeah. So you could say that valued outcome, of course, but a shared outcome in general of education is conceptual understanding. But it also has a bit to do about applying science in real life. That you learn to apply. You learn about mathematics and you learn to apply it at the same time. You learn to use it. So it's a bit more than conceptual understanding, but this is what it really adds to education in general, I would say. But a point to take into account. Teacher guidance, the teacher, when you implement it, need to be able to build on students' contributions, students' reasoning, try to connect to students' experience, to let them become owner of a problem. You need to do it in such a way that it connects to what they already know, what they have experienced. And the guidance is oriented on trying to motivate them to do the inquiry and to not stop, to get too easily frustrated, but guide their inquiry processes. There needs to be a classroom culture, that you are allowed to do your drawings even when you make mistakes. Making mistakes is not wrong. It's an opportunity for learning, because you learn from mistakes, and that needs to be part of the culture. When that's not there, then it becomes really difficult, because then students will not show quickly what they are doing, what they are thinking. It should be dialogic and collaborative. And the resources, meaningful learning situations the resources should involve students in the inquiry process, should be clear where in the task, what they are intended to do with respect to inquiry. Are they intended to formulate a question? Are they intended to plan a solution process? Or are they, it can be on different levels or on all levels, that you have a completely open situation. But that asks for big lessons. It can also be on small parts. Yeah.
Make sense for themselves. Why did you stress for themselves? Is there a special reason for that?
Yeah. Well, that was related to the aspect that in inquiry you try to understand and you try to formulate what you know.
I understand, but for themselves is stressed here.
Yeah. Well, at least it's on your personal level that you understand what's going on, what you're doing. Yeah, but you're right. Why makes sense in general, and also for others is important, of course, that you collaborate.
I can understand that in other sentences it can be added as well.
Yeah.
That's the classroom culture, shared sense of course.
Yeah. So maybe it's questionable to put that specifically there. Yeah, good question. Yeah, I need to remember. I have the video. I can recall it. Yeah, good. So that holistic view was also part of the starting point of this project, Mastiff project, where we built on the ideas of Primas, and we tried to use this idea of inquiry-based learning for diversity. And then diversity refers to not only diversity in achievement, but also diversity in culture, and that connected to, well, the recent awareness of inclusive education, that we need to really be aware of the changing classroom, where we have many cultures, and that we need to have a kind of inclusive classroom behavior. We need to try to create it. And there are different models for it, but one that I like is that you can look at, well, homogeneous classrooms, where learners are grouped in one kind of educational institution and are all more or less the same. Differences are not acknowledged, and that you can have heterogeneous classrooms where there are differences acknowledged, but you have created kind of level groups, and you provide support on the different needs of each of the level groups. But the most, well, complex one maybe is taking the opportunity of diversity. So they are perceived to be different, the learners, but that difference serves as a resource for your individual and mutual learning. That you take the opportunity of diversity instead of a challenge to be dealt with. And so this was also part of the background of this Mastiff project. In Europe, we have many cultures coming in, and especially in Germany and in Malta and in Turkey, where countries involved in the project, they said, yeah, we need to not to deal with it, but even take the opportunity of it. How can we use it and create also a sense of belonging of all these new children in our schools? Yeah. So taking the opportunity of diversity, well, there's a nice little video. I thought I would have more than enough time to show it, but time is running now already. Okay, but this is a nice video, I think, as a kind of metaphor to what we strive with when we try to see what helps for all students. And this is about chairs for airplanes, for the Marines, that need to be developed. And there were all different kinds of pilots, and the challenge was what kind of chair fits best. And well, the storyline becomes clear, I hope.
The issue is, how do you design one cockpit that can fit the most individuals? For a long time, it was assumed that you could do this by designing for the average pilot. That almost seems intuitively right. If you design something that fit for the average sized person, wouldn't it fit most people? It seems right, but it's actually wrong. And 60 years ago, an Air Force researcher, Gilbert Daniels, proved to the world just how wrong this really is and what it was costing us. Here's how he did it. He studied over 4,000 pilots, and he measured them on 10 dimensions of size. And he asked a very simple question. How many of these pilots are average on all 10 dimensions? The assumption was that most of them would be. Do you know how many really were? 0. Gilbert Daniels proved there was no such thing as an average pilot. Instead, what he found was that every single pilot had what we call a jagged size profile, right? Means you're not, no one's at the same on every dimension. And this makes sense. Just because you're the tallest person doesn't mean you're the heaviest. Doesn't mean you have the broadest shoulders or the longest torso. But this is tricky because if every pilot has a jagged size profile, and you design a cockpit on average, you've literally designed it for nobody. So the Air Force realized they had a problem, and their response was bold. They banned the average. Meaning that moving forward, they refused to buy fighter jets where the cockpit was designed for an average-sized pilot. And instead, they demanded that the companies who built these planes design them to the edges of dimensions of size. Meaning that rather than design for, say, the average height, they wanted the cockpit that could accommodate as close to the shortest pilot and the tallest pilot as the technology would allow. Now, the companies that made these planes, as you could imagine, weren't happy, right? They argued and lobbied, and they said it's going to be impossible, or at least impossibly expensive, to build a flexible cockpit. But once they realized that the Air Force wasn't going to budge, suddenly it was possible, and it turned out it wasn't that expensive. And in fact, they made great strides, leveraging simple solutions that we all take for granted in our everyday lives, like adjustable seats. And as a result, the Air Force not only improved the performance of the pilots that they already had, but they dramatically expanded their talent pool. And today, we have the most diverse pool of fighter pilots ever, but here's the thing. Many of our top pilots would have never fit in a cockpit designed on average. So, most of us have never sat in the cockpit of a $150 million fighter jet, right? But we've all sat in a classroom. And I would argue.
Okay. Well, you understand the point. I'm not sure whether I'm happy that we now have the opportunity of much more people becoming a pilot in a fighter jet, but I think the idea is so designing for the average or designing for the edges and making it possible to include everybody. That was one of our reasons why we thought that IBL is also helpful for taking the opportunity of diversity, because you don't have the risk of creating a fixed effect, which is also one of the problems, I think, with our differentiated system, where we immediately label students, or when you create level groups, that you label students. And with IBL, well, you can avoid offering one trajectory for all, the average, but involve all students to participate in activity and offer them the opportunity to work on their level. And then it also can provide teachers the tools or the opportunity to give level feedback. So this was our hypothesis about why IBL is helpful for taking the opportunity of diversity. So the research questions for this project were how can diversity and achievement and culture be addressed with IBL in mathematics and science education actually, and to what extent can teachers be supported in addressing diversity with IBL through a PD course. We designed a course and we used a kind of methodology where we had project team members giving feedback on initial versions, and we also had an international expert like Harry. He was not expert in this project, but in previous projects, and he knows the role of being an expert, that you sometimes are flown in, and you need to give feedback, and we also had him with this project. And walkthroughs by these teacher educators that were also part of the project, and tryouts. And it's all described in a paper so that you can find more details of how we did it. So topics of the course were diversity and achievement through IBL, use of multicultural context, and science and culture, how to learn it, and what it has to do with each other. And of course, first activities were trying to connect these elements to what the teachers' needs and what they already knew about how to deal with diversity, what they already have experience in trying to do inquiry in their classrooms. And we tried to build on that, and we also had some extra activities. And I give just a few examples of activities from the course. One of them was a kind of debate, that you debate with each other, statements about to what extent your discipline is neutral, or is it well, biased by your culture and your understanding. Does it have any relation with culture? What kind of scientists or mathematicians can you recall? Are they only male Western, or do you also know from Asia or Africa or other countries? And well, these were nice debates already, because especially you can imagine that with mathematicians, then the initial reaction was we have an objective discipline, but a neutral discipline, but then it turned out that also even there we could find things that are dependent of culturally biased. Another activity, there was one of the requests during these loops with feedback loops that we needed example of classroom materials that the teachers could also do with their students, and that you could let them work on it as if they were students, so that they could copy this kind of way of dealing with using a resource with their own students.